Welcome to Sticky Med, learning medicine, stick by stick.
Today, we are putting on our statistical detective hats and tackling a number that I know sounds a little dense, but it is absolutely fundamental to understanding medical research: the odds ratio.
It really is. I like to think of it as the ultimate tool for statistical time travel.
Time travel, I like that.
Well, the odds ratio, or OR, it's the mathematical instrument researchers use when they're looking back at a known outcome, like, say, a disease outbreak, and trying to figure out which specific factor is the culprit.
So this isn't just about crunching numbers, it's about how we assign statistical guilt in a way. If we have a disease as the crime scene, the odds ratio is how we find that solid, verifiable evidence linking a suspect and exposure to that outcome.
And our mission today is to break that down, not just conceptually, but mathematically, in a way that's, immediately actionable for you. We need to master three things.
And let's start with the context. We are talking about the statistic of choice for retrospective studies.
Meaning studies that look backwards.
Exactly. The disease has already happened. We're talking about case control studies. You find the sick people, and then you look back at their history to see what they were exposed to.
And that backward-looking approach is precisely why we need the odds ratio. To understand why, we have to kind of pause and unlearn the concept of probability or risk that most of us are familiar with.
Okay, let's do it. Let's unpack this using that analogy everyone knows, a deck of cards. So tell us how probability works in that scenario.
Okay, so probability, or you can call it risk, is what you calculate when you want to know the chance of something happening out of the total.
Out of everything possible.
Exactly. The formula is simple. Events divided by total events. So with a 52-card deck, the probability of drawing a heart is 13. That's our event, out of 52, the total.
Which is 25%, a 25% risk.
Right. It's relative to the entire population you're drawing from.
Okay, so now odds completely ignores that total, right? What does it look at instead?
Odds looks at the ratio of the event happening versus the event not happening. It's an internal comparison.
Okay.
So in that deck of cards example, the odds of drawing a heart are 13 hearts versus 39 non-hearts. The ratio is 1:3. We completely disregard the fact that the total deck is 52.
That makes sense mathematically, but why does epidemiology have to use odds? Why can't they just calculate the true risk? And this, I think, is where it gets really interesting.
This is the critical aha moment. In a case control study, the researchers they're essentially rigging the pool. They artificially select the subjects.
How so?
They might decide, okay, we're going to find exactly 100 sick patients, our cases, and 100 completely healthy patients, our controls.
So they've just set those numbers themselves. They didn't go out and find that, 100 out of 1,000,000 people got sick. They just picked the totals.
Precisely. They have tampered with the total population size, and because they pre-selected the number of sick people, they have completely destroyed the ability to calculate the true risk of getting that disease in the general population.
So any risk they calculate would be totally meaningless to the outside world.
Meaningless. Because the ratio of sick to healthy people they started with is completely artificial.
Got it. So because they can't ask, what is the true likelihood of becoming ill if you're exposed, they have to pivot.
They have to. They change the question entirely. They compare the only thing that remains untainted by their selection bias, the odds of exposure between the sick group and the healthy group. And that comparison gives us the odds ratio.
Okay, so we know why we're using odds and we know what we're looking for. How do they actually do the calculation? And that brings us to the classic tool, the 2x2 contingency table.
All right, think of this as just a simple four-square grid. We're categorizing people based on two things. Did they get the disease? Yes or no? And were they exposed to the suspect factor? Yes or no?
And we label these four cells A, B, C, and D. Let's make sure we define what those letters mean, without getting too jargony.
Okay, so A, this is the critical group. It's the intersection of exposure and disease. These are the sick people who were exposed.
Okay, sick and exposed. Got it.
B are the people who were exposed, but they didn't get sick. So healthy people who were exposed.
Right.
C, these are people who got the disease, but they were not exposed.
And then D must be the ideal comparison group.
Exactly. D are the healthy people who were not exposed.
So the beauty of the odds ratio is that it compares two internal ratios from this table. Conceptually, it asks, what are the odds that a sick person was exposed, which is A divided by C?
Right.
Compared to the odds that a healthy person was exposed, which is B divided by D.
That is the conceptual heart of the formula. But if you look at that equation, AC divided by BV it looks a bit complicated. This is why researchers use a fantastic shortcut,
The cross product.
the cross product.
I love this because it makes the math so simple you could do it on a napkin. Instead of dividing fractions, you just multiply the diagonal corners of that 2x2 table.
That's it. It's A times D divided by B times C. You're comparing the product of the two groups that fit the hypothesis, really sick and exposed and healthy and unexposed, against the two groups that buck the trend.
And once you do that quick calculation, you get a single number, the odds ratio.
Yep.
Okay, now for the real power interpretation. If I calculate an OR of, say, 7.3, what does that actually mean?
It's always a multiplier. It
Yeah.
tells you how many times more likely the outcome is. And we interpret everything against the fulcrum, the null point, which is the number 1.
The rule of one.
The rule of 1. If you remember nothing else, remember that 1 means absolutely nothing happened, no effect.
So let's walk through the 3 possible interpretations.
Sure. 1. Or 1. This is the null value. The exposure did absolutely nothing. The odds of being exposed were exactly the same in both groups. No association.
Okay, what if it's bigger than 1?
2. Or are 1. This is a risk factor. The exposure increases the odds of the disease. So an OR of 5 means the odds of having the disease are 5 times higher in the exposed group. That's a strong association.
And then the opposite must be true for less than 1.
Exactly. 3. Or are 1. This is a protective factor. The exposure decreases the odds of the disease. So an OR of 0.5 means the odds of getting the disease were cut in half by that exposure. Think vaccines, healthy habits, things like that.
That makes perfect sense. But in every research paper I've ever seen, that single OR number is always followed by the 95% confidence interval, the CI.
And it's useless without it.
Why is that?
The CI is the statistical reality check. It tells you if your result is truly meaningful or if you just got lucky with a random sample. Think of it like aiming at a target. The OR is the bullseye where your dart landed. The CI is the margin of error, that surrounding ring that shows how accurate your shot was.
And if that ring is too wide, you can't be sure you really hit the bullseye.
That's it. And the rule for interpreting the CI is simple. The entire range must be on one side of our null value, 1. If it crosses 1, the result is inconclusive.
Okay, so it can't touch or cross 1.
Right. Let's run 3 quick examples. A strong positive finding. OR is 3.5. And the CI is 2.1 to 5.6. The entire range is above 1. So we're statistically confident this is a real risk factor,
Makes sense.
a strong protective finding. OR is 0.5, and the CI is 0.2 to 0.8. Again, the whole range is below 1. It's a significant protective effect.
But what if it crosses?
Okay, so what if the OR is, say, 1.8, but the CI is 0.8 to 2.5?
It crosses 1. The bottom of the range is 0.8.
It crosses 1. So even though 1.8 looks like a risk because the interval dips below that null value, we can't rule out the possibility that the real answer is 1 and our finding was just due to chance.
Yeah.
That result is non-significant.
That explanation really helps. The confidence interval is the filter for separating noise from the signal.
It keeps the statistical detective honest.
Okay, let's put this into practice. We're investigating a scenario every epidemiologist dreams of. An outbreak of some nasty gastrointestinal distress at a wedding. And the prime suspect is the shrimp cocktail.
A classic.
Yeah.
So we immediately set up our case control study. We find everyone who got sick our cases, and we match them with an equal number of people who felt fine our controls. Let's say we have 50 cases and 50 controls.
And we interview them all about the shrimp. Let's lay out the data for everyone listening so they can visualize that 2x2 table.
Right. Of the 50 people who got sick, 40 of them reported eating the shrimp. 10 did not.
Okay. And of the 50 people who felt fine,
Only 10 of them ate the shrimp, and 40 of them successfully avoided it.
let's map those numbers onto our A, B, C, D quadrants then.
Okay.
A, that's sick and exposed, so people who ate the shrimp and got sick. That's 40.
40, yep.
B is healthy and exposed. Ate the shrimp but felt fine. That's 10.
10.
C is sick but not exposed. Got sick without eating shrimp. Also 10.
Mm-hmm.
And D is healthy and not exposed. Avoided the shrimp. Felt fine. That's 40.
Perfect. A is 40, B is 10, C is 10, D is 40.
Now for the quick math, the cross-product shortcut. A times D divided by B times C.
So we multiply A times D, 40 times 40, which is 1,600.
Okay, and then we multiply B times C, 10 times 10, which is 100.
100. And then the final division, 1,600 divided by 100.
Which gives us 16. The odds ratio is 16.
And just look at that result through the rule of 1. It is overwhelmingly greater than 1.
So what's the clinical translation? How do you say that?
It's immediate and it's powerful. The odds of having eaten the shrimp cocktail were 16 times higher in the sick people than they were in the healthy people.
The shrimp is guilty.
The shrimp is guilty. That's the speed and specificity the odds ratio gives you.
That's a fantastic example, but let's step into the last bit of nuance here, which is a key point. The difference between the odds ratio we just calculated and the relative risk, or RR.
Right. And this is a fundamental distinction because relative risk is probably the statistic that most people intuitively understand better.
We already established that we use the OR for these case control studies, so when can you use relative risk?
You can only calculate relative risk in cohort studies. A cohort study is the opposite of what we've been talking about. Instead of looking backward, you look forward.
Okay.
You identify a huge group of people, a cohort, and you track two subgroups, those exposed to a factor and those not exposed. And then you wait, sometimes for decades, to see who gets sick.
Right. And since you're following a true population forward, you haven't artificially messed with the numbers of sick people, so you can calculate the true risk.
You can. So relative risk is just a direct comparison of those two true risks. It's much easier to explain. You can say you have 5 times the risk of getting sick. But you can imagine the studies are incredibly expensive and slow.
Especially for rare diseases, you could be waiting a lifetime.
Yeah, exactly. So we are often stuck using the faster, cheaper retrospective method, which means we're stuck with the odds ratio. Which leads us to this little saving grace that connects the two, the rare disease assumption.
The rare disease assumption.
This is a really elegant statistical rule. It says that if the disease we're studying is rare, and epidemiology generally considers rare to have a prevalence of less than 10%, then the odds ratio mathematically converges on the relative risk value.
So for things like a rare cancer or a very specific side effect from a drug, the OR that we calculate becomes an excellent, trustworthy estimate of the true relative risk.
It becomes a fantastic proxy. Even though we started by measuring odds because we couldn't measure risk, the math means we end up with a reliable stand-in for risk anyway.
Why does that work?
Well, it's pretty simple, actually. When the number of sick people, A and C in our table, is very, very small compared to the healthy people, B and D, the denominators in the two different formulas become almost identical. And when the denominators align, the ratios align. It's a lifesaver for rare disease research.
So we've successfully unpacked the odds ratio. It's the essential detective tool for these retrospective studies. We figured out why we have to abandon our normal idea of risk and rely on this internal odds comparison when we've artificially selected our population.
And we navigated the 2x2 table and found our compass in the rule of 1.
And we learned that while the OR is, it's a necessity in case control studies, it becomes so powerful because of that rare disease assumption, especially when we're studying serious, uncommon conditions. And this, I think, leads to an important final thought.
Go on.
Think about how often we must rely on odds to infer certainty in medicine. When you hear a headline claiming some exposure increases your risk of a rare condition by 15%, well, that risk value is often just an odds ratio doing a heavy lift as an estimate. It raises a really important question about how our understanding of danger is built on this complex but incredibly robust statistical architecture.